Okay, so this is just a brief addendum to the last lecture where we did the glycolysis model. Remember, we did the glycolysis model. It's a model for burning basically glucose in your body or in any plant. We analyzed the model. We did the null clines. We put them on the plot. So there the two are. We did the whole linear analysis. We put the fixed point on, and we've looked at when it becomes stable and unstable. And then the most of last time is we designed this trapping region that basically consists of the x-axis, the y-axis up there, this line, y equals to b over a all the way until the x value b, and then the line x plus y equals to a constant. In other words, y equals to minus x plus a constant. And we worked out what that constant was over here so that it would hit this point and that all the arrows would be inward. And then we said this was a trapping region. It's a finite trapping region. And I just want to show you what the actual integrated solutions look like, right? So we did all the parts of the proof for making the trapping region. We had the box so everything goes in. We cut out all the fixed points, and we could only cut them out if they were unstable. And we then used the Poincare-Bendixson theorem to say if it's unstable, then we have a limit cycle. So I actually want to show you what the limit cycle looks like, and that you can't do by analysis. That I'll never ask you in a test, except if there's an analytic method to get it, or I'll guess it for you. But you can do it with a numerical code that I gave you in the previous thing. And so that's just basically what I did, is you go about, you replace a differential equation. Now it blew my thunder. You basically replace this differential equation up here with, in the code, you give values for A and B, and then you draw it. And I said the reason I did the linear analysis first the last time was that, remember, we said that this is the curve that determines whether the fixed points are unstable or stable. Okay, so this fixed point in the center, we showed it was unique, and we worked out the curve in AB space where it was unstable. So I'm now going to show you what the thing looks like if you start with, there we go. If you start with an initial condition that lies just outside the unstable region. So over there where that blue dot is, it's just below the black curve. So that's the place where tau is less than 0, and therefore we have a stable fixed point. Okay, so if we have a stable fixed point, we know we're going to draw that plot again. So this is the plot that we drew so carefully on the previous time. We know that it's going to enter. We have this trapping region where the thing is going to go into, and we know it's going to stay in there. And then we basically have two possibilities. It either goes to a fixed point or a limit cycle. And only if you've cut out all the fixed points can you prove that it goes to a limit cycle. Okay. And if the fixed point is stable, we can't cut it out because all the arrows around it point to the fixed point. So in this case, if you start anywhere, your trajectory is basically going to go, it's basically going to follow the arrows over here until it hits the null cline. At the null cline, it goes vertical. It makes a bend because when it hits the next null cline, it's got to be horizontal. It follows the arrows. Over here, it starts turning up until it again hits this teal null cline where it's got to go vertical, goes up, hits the next null cline where it's horizontal. So you can see the null clines give you a very good idea of what the shape of the orbit's going to be. And then it basically goes around and it spirals in, and eventually spirals in very, very slowly, but it hits the fixed point. Okay, so no limit cycle if we're outside of the red region. And then just the final plot, I want to give you show you what happens if we now choose our little dot in the red region. Okay, so this one's just a stable spiral, no limit cycle. If we now move that blue dot up just a little bit, and there's such that it's just in that red region, and we again do the same thing. So we again plot everything we had the last time. You can see when our parameters change, the shape of the graph changes, right? A and B is different from the previous plot. But the basic features we've got in there don't. right? So the null-clines are still there. The fact that you're going in over the x-axis is still there. So everything you drew is fine. It's just that the numbers or the shapes have changed slightly. See, this fixed point is still after the hump, but it's just moved slightly to the right. The square root a have moved apart, and you still have this, the point where the fixed point occurs, and you still have that everything moves inward along this thing and inward along that thing, and the trapping region is still entirely valid because you did it in terms of the parameters. But now, because it's actually an unstable fixed point, we can put the dots around it, we cut it out, and in fact, let's see what happens if we start really, really close to the fixed point. So we're just going to start epsilon away from the fixed point, and what you're going to do is you're going to have this unstable spiral. So this trajectory, I started in the fixed point. You can see it spirals out, taking into account the shape of the null-clines, and it's going to go somewhere, okay? But you know it's never going to get out of that dotted box you built it, so it's going to eventually get stuck somewhere. And so let's let it go on, let it spiral out further. It keeps getting bigger and bigger, and eventually it's going to get stuck. And where it gets stuck is exactly where your limit cycle is. Okay, so the unstable spiral basically then expands, goes through the center where everything would be concentric circles, and then it gets unstable, and then it basically makes a limit cycle at a particular round orbit. Right, suppose now we were to start outside of the box, outside of the limit cycle anywhere. So I'm just going to clear everything, all the spirals on the inside to make sure I don't cheat. To actually make sure I don't cheat with the thing. So I've cleared all the spirals inside. I've left the limit cycle. So let's start, say, over there, and you can see this thing very, very rapidly approaches the limit cycle in a way that's consistent to what we expect, right? Vertical on the teal null-cline, horizontal on the sort of light purple or mauve null-cline, and then it goes round and approaches this egg shape until it eventually, you can see there the blue almost just lies just outside the limit cycle, and eventually it'll lie on top. Let's start at a different spot. Okay, where have I started now? Right, so if I start over here, right, I deleted the other one. If I start over here, I do the same thing. I just go up, I go a little bit higher, I go around, and I spiral in. Remember, trajectories in 2 dimensions can never cross each other. Okay, so the other one would fit nicely in between these two, as you'll see when I put them all on the same plot. Just another one, if I start over here, it's going to do the same thing. It's just going to go up a little bit higher and then fit neatly in between this limit cycle over here. Start at a different place, does the same thing. Null-cline horizontal, null-cline vertical, and then spirals in, but it gets stuck over there at the fixed point. At the limit cycle. Start even further away, you have the same thing. So the pace at which it goes in is sort of fixed by all the other limit cycles together, but it always approaches the red one. Okay, there's another one, this one that I started out here. It just fits in below this thing and then goes round and goes in. Never crossing the limit cycle, always getting stuck there. And now I've just put in the ones that spiraled out towards it. Okay. So there we go. That's just a little bit I wanted to add to the last lecture, and I'm going to stop lecturing now and then look at some of the problems. But yeah, it's a very, very powerful thing, this idea of the Poincare-Bendixson theorem that traps your limit cycle, and it's very, very useful. And a lot of physical systems that are interesting actually use it. And we'll come across more of them as time goes on. Okay, let me just...